Okay, so yeah, time for our second talk of today. So Charlotte is going to be talking about some very cool work that she did as a bachelor's student working with Johannes. And yeah, whenever you're ready, Charlotte, please take it away.
Oh, sure. Thank you. Thank you for inviting me. So yes, as you just said, I'm going to talk to you about my work from when I was a bachelor's student. So I am in no way a BXA expert, but maybe by showing you my project, you can get some inspiration or maybe some motivation to do some stuff of your own with BXAs. So thanks to the previous talk, I won't have to do much of an introduction to AGN, which is great. Because this whole project was about getting redshifts from obscured AGN. In this project, though, the AGN, we see them as slightly simpler than in the previous models. So just look at it as a supermassive black hole that is accreting, and then it has this torus around it. But it's not very important what's happening in this torus, if it's clumpy or how the dust is. So let's go. So motivation, also you're going to see a lot of skeletons in my talk. So why did we choose AGN to study? Well, the first thing is that most massive galaxies are expected to have a supermassive black hole in its center, and the growth of that black hole is linked to galaxy evolution. So in order to study them, we need reliable redshift measurements. So like new missions like JWST, part of their main science goals is to understand how black holes grow. So it's quite important. Now, why do we need them to be obscured? The previous talk went through this a little bit, so I'll try to be brief. But basically, to the first order, an AGN, if we were looking at it unobscured, if it was directly looking towards us and not going through a torus, we would see that the X-ray spectra is to the first order just power law. So no futures, it's quite smooth. But once we have obscurations, some things start to happen. So there's mainly three things that could happen to a photon. That is a hard photon coming from the corona of the supermassive black hole. It will go through some gas and dust, and there's basically three things that can happen to it. So first, it will either be scattered around, or it will be affected by photoelectric absorption, which will either lead to a fluorescent line, which we will use in our case, or it will just be destroyed. So a combination of these factors makes the spectrum not be smooth anymore, but have some features that we can use to get some information about redshift. So why do we need a new method to estimate redshifts? We do have spectroscopic redshifts that we call SPEC-C in this work, and we also have photometric redshifts. And these are all great, but SPEC-C has some issues in that it is expensive and it's time consuming. And counterpart associations can be ambiguous. So what do I mean by this? That in these images, the red circle is centered on X-ray position and errors. And you can see that in these cases, there are two objects that could be associated to that X-ray emission. So if you're getting your redshift based on your counterpart, then you might be getting a very good redshift, but you're looking at the wrong object, basically. So you're getting a redshift that is not from where your X-rays are coming. And then we have photometric redshifts, which are much cheaper. Photometry is much easier than spectroscopy. But then we have issues like sources can be variable, which AGNs we know can be. There can be mixing of the light of the AGN with the light from the stars of the galaxy, which can be very difficult to disentangle. And we often have multiple solutions. So how do you choose which is the correct one? It's not always obvious. So this is why we introduced this new method that is to obtain redshifts, but using X-ray spectra. So low resolution X-ray spectra, and it is to be used as a complement to the other methods. For example, a photometry that you're uncertain, or SPEC-C that was just done using one emission line, so you're not really sure what the redshift is. So from now on, I'm going to explain a bit this method, but this is a short talk. I'm not going to go very deep. So if you want, as this is a school, if you want to know the specific commands I used in Sherpa, just write me in Slack. I can give you some snippets of code and tell you what we used for the work. So our AGN model, from now on, we use the Taurus model from Brightman and Nandra. And this is, again, much simpler than the ones presented in the previous talk. But this is a supermassive black hole, and it's basically a sphere that has a cutout shaped like a torus. And then you can input things like inclination angles to get your different viewing angles. And from here, you will get that the power law spectrum that comes from the corona of the black hole will be either transmitted or reflected, which was also shown. And this model computes a spectra, including the 3 effects that I mentioned previously, which is quite cool. Sorry. And when we look at the spectra, it looks something like this. So on the right side, I show 4 different curves of X-ray spectra. And from top to bottom, we increase the column density of hydrogen. So we make it more obscured. And you can see that for the lightest one, that's 22, there's basically no features there. But as soon as we start going to higher obscurations, all these effects that I mentioned previously start to be prevalent. And in particular, we get a fluorescent line at 6.4 keV, which gets very prominent as it gets more obscured. So that's one of the main places where we get our redshift information from. And that's why we also need them to be obscured, because else there's nothing to grab onto. So we use this Taurus model, but we combine it with a soft scattering power law and include galactic absorption, very similar to what was shown previously. This is the model that Johannes used in his paper in 2014, and it works quite well for the data from Chandra Deep Field South, which is what we use for this work as real data. So from now on, this is what we used as a model. So in order to test this, we use both data and simulations. So the data, as I said, is from the Chandra Deep Field South 4 megasecond AGN catalog. So these are about 300 sources. And then we created fake data for Athena, Chandra, Eurosita, New Star, Swift, and XMM. We varied the obscuration, we varied the redshift, and we varied the amount of counts for each instrument. And then what we did was grab everything and fit them all. So we used Sherpa, you could perfectly use XPEC as well. And we fit the torus, but we also fit the background. So we jointly fit both things, which improves our results. The background was a auto background fitting tool. It's called BStat. If you want details about BStat, though, you should ask Johannes. So we did this for all our data and for all our simulations. And the main parameters that we were looking for and that were fit simultaneously were the column density, the redshift, and the photon index. So we use non-informative priors as much as possible. So in H and redshift, we used a log uniform prior that varied between 20 and 26, and 0 and 7, as is shown on the bottom right on my screen. And the photon index, though, we used a Gaussian prior, and this is based on the work of Nandra and Pounds. It seems to work quite well. So it's a Gaussian with a mean of 1.9 and a standard deviation of 0.15. And what I'm showing you here are posteriors. These are 2 examples of our real data, which are really nice in the sense that the gray one is mildly obscured, but has a high amount of counts. So it has like almost 6,000 counts. So you could get a really good fit from that. and get absorption edges, even if you don't necessarily get a strong iron K alpha. And then the blue one was heavily obscured with much lower number of source counts. So in this case, it says 129, but it was 128 counts. And so if you look at how the counts are distributed, you basically see 100 counts just everywhere, but there's a bit of a amalgamation around the 6.4 kV line. So that's where it's getting the information from. So these are two cases that are quite different because they have different NHs and different amount of counts, but XZ worked for both of them. We do note, though, that there seems to be maybe 2 solutions in the blue case for NH. So sometimes there might be multiple solutions going on. And since we know that there might be multiple solutions, we have to find a way to quantify our results. So as has been said on the school before, it's a really iffy thing to say a goodness of what do we really mean if the fit is good or not, if the result is good or not. But what we used here is how much information did we gain as a quantifier. So we use the full redshift probability distributions. We don't just look at the peak at one number. So if this PDF only had one peak and it had a very small standard deviation, we would say it's constrained. The redshift is constrained. We're not saying if it's right or wrong. We're just saying the code is giving us a constrained result. Now that's much more difficult to see when you have multiple peaks. So how do we deal with that? And we use the Kullback-Leibler divergence. The formula is there, but the easy explanation, it's just a way of quantifying how different your posterior are from your priors. So in our case, we tried to use non-informative priors. So if we got an information gain of 0, it would mean that our posteriors are equal to our priors. So we learned nothing. But as soon as that starts improving a little bit, we get some information. So we created this criteria that's in the bottom, that if the information gain is less than 1, we have little to no redshift information, which doesn't mean it's useless because you can always combine it with photo Z, for example. Then we have between 1 and 2 bits that we get some redshift information, and then information gain above 2, we say the redshift is constrained, which doesn't mean you should trust it blindly, but it means the code is quite sure of what it's spitting out, basically. But this would always, if possible, be used with other measures as well. So when we look at the data, we have 23% of redshifts that were constrained in the CDFS data, and 20% that had some information. So on the right, there's a plot that shows on the y-axis XZ, which is our X-ray redshift measurements. And in the x-axis, it shows the spectroscopic redshift from literature. And the color code is just the obscuration. So the super pink one is heavily obscured. And by y, at least, we can see that these kind of agree quite well. However, we can see some points here and there that have very small error bars. Like, for example, I don't know if you can see my cursor, but there's a point here, a purple one in the middle, that has very small error bars, but it's not in the 1-to-1 relation. So those are quite interesting to look one-on-one. So we analyzed this and we found 5 cases where we suspect that there's an incorrect spec C, which was quite fun. So how we identified these cases was we looked at the PDF of XZ and we looked at photo C PDFs, and then we noticed that the photo C didn't agree with spec C. So we wanted to see if maybe XZ could give us an answer of which one was right. So in these plots to the left, these are 5 different galaxies with the information gain and the title. The orange lines, vertical lines, are all spec C. So they're quite different. And all the green ones are photo-C. So in all cases different. And the blue one with the square, that is XZ. And we find that in 2 cases at least. We found updated species, which are the black line here and the black white line here. So in this case up here, XZ wasn't exactly on the right solution. But if it had to pick if it was a high or a low redshift solution, it at least could identify which one was more probable. So it's quite useful to use it as a tool in conjunction with others. Now, if you're wondering how spec-C could be wrong, because spec-C is in general quite accurate, one of the common things that can go wrong is that it might be reported as being very confident, but then if you go to the source, they just used one emission line. And that is quite risky to seal a redshift down confidently with one emission line. Then for the fake data, we looked at the sensitivity limit of XZ. So if you're more interested, you can go to the paper to see each instrument, how many counts you need in order to gain some information. This is just a summary plot. And so this is basically how luminous in 2 to 10 keV a source would have to be at different redshifts in order for this method to gain some information from redshift for each instrument. So this is the limit in order to get information gain above 1. And to my understanding, it's being used today by some groups, which is pretty cool. So yeah, my final thoughts would be that it's a quick tool that uses low resolution X-ray spectra to obtain redshift information. And the sensitivity depends on both the count number and the obscuration. And there's a bit of a power play between those two, as I showed you previously. This is different for each instrument as well. But one of the very nice things is that if you don't need the right conditions, it doesn't mean you're going to get a wrong result. You're probably just going to get a really large error bar, or you're just not going to get any redshift information from it. So having said that, I'll just leave you with this. What can you do with BXA? So yeah, thank you.
Thank you very much, Charlotte, for a very nice talk. So is there anyone in the room that would like to ask a question? Yep, we have a question from Angel.
Yeah, I was wondering, following what we saw in the previous talk about the dependency of the estimation of spectral parameters with the Taurus model, if you actually check how dependent is the calculation of the redshift that you assume.
I'm not sure I understood everything you said because you cut out. You're asking if we use a different Taurus model, if the redshift would change?
Yeah.
Is that it?
Yeah, that's it.
Well, that would be very interesting to check. It's not something I am working on right now, but maybe it would be something that someone working with it currently could check. I guess that, yeah, but my feeling is that I don't think it would make too much of a difference based on what we saw in the previous talk, but I can't give you a definite answer.
So actually, I had a question kind of linked to that. So I really like this method, and I was like, please correct me if I'm wrong, but is it the case that essentially you're treating torus parameters as almost nuisance parameters, right? That you marginalize over to get the redshift, if that makes sense.
Yeah.
Yeah, so you're kind of relying on having a line and a nice edge somewhere that you can fit with a typical, say, reflection spectrum.
Yes.
And so the things, I guess the torus parameters that change the shape of that spectrum are more, you know, in other works, they may be treated as something you're interested in, but it doesn't matter for this method, which is really cool, actually. Yeah. Yeah. Okay. Are there any other questions in the room? No? Any comments? No? Were there any on Slack or on the chats? No?